another kind of CFT on the worksheet which has a BRST differential. But something has a nilpotent symmetry which can behave as a BRST differential, even though it's not built from ghosts and matter fields. And then you can repeat the usual procedure and you get some kind of string theory. This is not, this is a pretty bizarre string theory from the point of target space, but it can capture some protected sectors in superstring theory. So there are some pieces of superstring theory which can be computed using this topological string theory.
If there are no ghosts, how can be T exact?
So there is another operator there are other two operators whose anticommutator gives you T. So it comes from what's called a twist of a superconformal field theory. Superconformal field theory translations and things like that are anticommutators of fermionic symmetries. And if you can pick one of those fermionic symmetries as your BRST charge, then you can make the stress tensor exact. In a sense, there are many ways to sort of to make a string theory. You need a theory in the worksheet which is kind of topological in some BRST sense. The stress tensor is exact. There are various ways you can produce a topological field theory in 2D. Bosonic string theory does it by taking a CFT and coupling it to gravity, essentially. Perhaps I should say conformal gravity, because we get rid of wild invariance too. And once you have gravity, your system is kind of topological, because you cannot talk about location of things anymore. You can do this sort of twisting of supersymmetric theories. Or perhaps you can use other technology. OK, so let's start the lecture. Do you have any questions about last lecture? I know it was a bit compressed. So let's uncompress some of it.
Yeah, so sometimes when I gauge tricks, I'm left over with like an integral over like 0 modes, right? That I didn't sort of gauge fix away, I guess.
Yes.
And then I sort of insert by hand these 0 modes into the path integral to sort of get rid of this extra integral, right? But like, is there a way of not inserting it by hand and somehow getting it for free? These extra insertions of like C ghosts and stuff like this.
So in principle, you can do whatever gauge fixings you want, right? But some gauge fixings might really hide properties of the quantum field theory that you care about. Locality is a particularly important property. If you do gauge fixings which are not local, then I would really worry about preserving locality after quantization. It might still happen, but it seems unnatural. So in order for your gauge fix theory to be a quantum field theory, sometimes you need to make choices which do not allow you to kill all gauge symmetry. So there might be sort of some gauge symmetries which are global on the whole space-time, and just you cannot kill them by doing something local in every point of space-time. This is what happens when we gauge fix the diffeomorphism invariance on the worksheet. There are some modes left. Which modes are left depend on the global structure of the worksheet, and we just have to live with that.
Okay, but and then I sort of insert some C ghosts into the path integral to get rid of them or something like that.
Yes.
But is there sort of a way of getting these C ghosts for free so that I don't have to insert them by hand? Or,
I don't know if it worked by hand. He's the right word here. It's not that you're putting them by hand. It's that in order to get a non-zero correlation function, you have to insert operators with various ghost number. and these choices will have a meaning. Right. So if you find yourself in this situation where there are these zero modes of B's and C's, especially the ones of C's, let's say this. I mean, it really depends on the situation. I'm not sure I can make a universal statement. Because it really depends on how you're going to then in practice deal with these extra ghosts. Now, I should stress that in string theory, this is not going to happen typically. So let me explain. If you look at a surface like this, and you place some reasonable states, like these ground states we were talking about, we will find that actually you do not have unfixed symmetries. So vector fields, holomorphic vector fields on this surface. So on a sphere, you have holomorphic vector fields. But on the surface, there are no holomorphic vector fields which do not blow up along these directions. Or that, that satisfy whatever boundary conditions we want at the end of the cylinders. So let me try to explain this better. I don't want to introduce the state operator map before I introduce the state operator map. That's the only. So I will leave it for later. But I just say that you can try to write down a holomorphic vector field that doesn't grow exponentially fast, and you will fail. So the problem of inserting C ghosts is not there in computing string theory amplitudes. It sort of only appears in some intermediate phase of the. So, yeah, it just doesn't happen. The B ghosts, on the other hand, they're definitely there, but those are not arbitrary insertions. They are precisely tailored to build the measure on the integration on the space of compact structures. So you never find yourself putting in some ghosts by hand. When we map this calculation to the sphere, on the sphere we will have to see some ghosts because the sphere has this, but the ghosts will not come by hand. Just will be contained by the image of this ground state or these states. So when we learn that state operator map, we learn how to replace these infinite tubes with operators at points. Then the ghosts will come out naturally. We will not have to put them by hand. Other questions? Okay, so where are we? We learn how to define the space of states for the CFT of the axis and the auxiliary ghost system that comes out of gauge fixing. And the Hilbert space consists of, on the cylinder, consists of some ground states, which are labeled by momentum for the axis, and this choice of ground state for the ghost that we discussed. And then we can act on these by any number of raising operators for the scalar fields and B's and C's. This is a gigantic space. In order to get the space of states of string theory, we are supposed to take the kernel to introduce this Q. Which is the zero mode of a certain current. And sorry, I always forget to write it, but we also need, we both need holomorphic and anti-holomorphic modes. And the Hilbert space of the string theory string perturbation theory is going to be the kernel of Q acting on this space divided by the image of Q. So we take states which are in here that are annihilated by Q, and then the ones that are in the image of Q we treat as a sort of gauge redundancies. This is the sort of the proper way of doing the thing we did by hand, of saying, okay, I look at states which are killed by the constraints, by half the constraints, but throw away the ones that are orthogonal to the physical ones. So we remember in some lecture we're doing something like physical states divided by null states. This is the proper way to do it. Now, the problem looks very messy at first. This Q can do all sorts of things to states. But, and yes, there might be some bizarre cohomology classes here that involve a lot of ghosts in a complicated way. But the ones that are most interesting for us are actually pretty straightforward to describe. We can start looking at states which look like this. They have, we just act with A's on P, G, and do not try to use ghosts, at least at first. Let me call this just sort of some physical state tensor with the ghost ground state. So I can ask, where does it go when I act with Q? So Q does not raise or lower the energy, it's a zero mode, and it adds a C. So also the only thing that acts on the physical states, on the things built out of in this sector, is the modes of the stress tensor. You take the zero mode part of these, you get something like a sum of Cn, C minus n Ln. Maybe let me say let's Cn L minus n, or vice versa. Sorry, doesn't matter, same thing. So, and only the C's that construct some, that raise the energy will be able to act on the ground state or the zero one. So one term that you can find here is pretty much sum of C minus n, n greater than equal to greater than 0, Ln on the physical state, and then there is this mess of stuff, but this only acts on the ghosts. It leaves the energy the same. It raises the ghost number by 1, So I can only send G to C0G. So here there was a term that was something like L0, C0. And then I need to check by hand what this does. And it's not hard to do, and you get minus C0. So plus stuff involving C bars and L bars. So you see now that the condition for this state to be killed by Q is pretty familiar. It will have the physical part of it will have to be killed by the half of the moles of the stress tensor, and it will have to satisfy to have a very specific energy. These are the same condition I wrote down when we were doing things by hand, studying the spectrum by hand. So sort of the kernel of Q definitely contains something that looked like this, the physical states I was discussing. Now you can also now look at the image of Q. This is a little messier. If you remember, the things we were calling null were things of the form L minus n on a physical state, right? So you would like to show that null times G is in the image of Q. Sort of and yes, you can show it, but it takes more work. Sort of, if you act with Q on something like physical times G, right? I'm going to get terms which, sorry, I want to say it properly. So suppose I act Q on Cn of physical tensor G. C minus n. B minus n, sorry, my bad. Now, this term acting on it can cache the B. So this will contain a term that looks like Ln, physical state, tensor G, which are the null states. But there are also other terms involving bilinear sort of ghosts, things like, I don't know, B minus n Cm L minus m of the physical state. Etc. So what one has to show tediously is that you can systematically correct what you're doing here in order to eliminate the extra stuff. Okay, and this sort of can be used to show that the procedure we were using to discuss physical states modulo null states pretty much reproduces kernel modulo image of Q. This is sort of there is a theorem that one can prove that this is the case. Okay. So at this point, it means that in this formalism, this BRT formalism, we know how to talk about things like this tachyon or this graviton or whatnot, all of the states we saw in the spectrum of the bosonic string. What we are left to do now is to learn how to input this information in the picture I just erased. So how do we ever go how do you compute as if, a correlation function like this with a bunch of physical tensor G placed in each external leg, and a choice of complex structure and an integral over the space of complex structures. So this is what we have to now learn how to do. And the first step is to sort of go from a surface that looks like this to something that we can think about more easily. So we need to learn how to get rid of these semi-infinite tubes. And here is where the state operator map comes in. This is a very important concept in conformal field theory. So it sort of deserves its own discussion. So we'll spend now some time discussing interesting Weyl transformations. Interesting games you can play with metrics. Let's see where we can start. Let me start like this. So let me start from the plane. The plane has a metric which in complex coordinate is the z bar. Is this a familiar statement? I probably forget it's a factor of 2 pi I. Then be concerned with that. I'm going to do a Weyl transformation. Actually, sorry, I should ask this. Have you seen the state operator map perhaps in some of the some lectures in some other course? Okay. I'm still going to go over it, but it's good to know that it's not completely new. I'm going to do a Weyl transformation which is singular at the origin. Okay. Can you guess which space is this? What is this a metric that you might be at all familiar with? Mm-hmm. How would you see that? How would you demonstrate that?
R e to the I theta probably then.
Yeah, that's good. Let's start with z. Let's pick coordinates z, polar coordinates. And this becomes the usual polar coordinates metric. Oops. Divided by r squared. Is this about chalk or about Blackboard or what? So now we see a circle, and we see something else. Now I can do r equal to e to the t, e to the tau. And this becomes d tau squared plus d phi squared. Maybe I should call this sigma, but I'll leave it at that. Okay, and then we can recognize the cylinder in complex coordinates if we write them up as z is equal to e to the s. I wonder if it was s or minus s. What's the natural one? Not that it matters, but just wanted to be consistent. Yeah. Okay, so we related the plane to the cylinder. Now, as the theories we're studying are supposed to be well invariant, this suggests that there should be a way to relate correlation functions on a cylinder and correlation functions on the plane. Right. We can check if this is true. So we can go back to say, let's see. Let's try to see. Now, in order to define a correlation function on a plane, I need to give a choice of vacuum, strictly speaking. We could get in a lot of confusions there. The plane can be a confusing place to work with the conformal field theory. But for the Flory scalar, I'm not too concerned. So let's say, for example, the correlation function of dx dx on the plane. What is that? Can we figure it out? You might have seen it. Or you can derive it from some sort of uglier two-point function of the scalar field. I forget it's a plus or minus. So the scalar field is a terrible thing in two dimension, the correlation function of the scalar field, because they have these logarithms. But once you look at the current, things are so much better. Can you get this from here?
1 over z minus.
Yes, that's right. It is sort of the only thing you could write down that is translation invariant and has a correct scaling symmetry, because this is dimension 1 under scale transformations. Okay, let's map it to the cylinder. So the zx equal, so the sx, sorry, is the zx del z over del s. So it's e to the s del zx. So if I want to, so this maps to a correlation function that looks like this. I have e to the s plus s prime over e to the s minus e to the s prime squared. Now, at some point, we were computing correlation functions on the cylinder, and we did get something similar to this, but we got this from a very specific state as an expectation value in a very specific state, which was the ground state. So what this really maps to is an expectation value on the vacuum state, on the ground state on the cylinder. Now this begs the question, what if I look at a correlation function? And notice I'm writing this, but there is something, there really should be a delta function of 0 in here, right? Because remember that on the cylinder we have delta function normalizable states. So what's going on is that here there was also secretly an infinity because the expectation value of 1 is kind of infinite because it's a free scalar. It's like it's a free scalar. The zero mode is unconstrained in this expectation value. So there is going to be sort of an infinity put somewhere. But strictly speaking, this is always defined as dividing by the partition function without any correlation functions, without any operator insertions, which is a bit arbitrary. So what it really gives you is the ratio. Okay. But anyway, let me leave that aside for a moment. The question is, how would I ever reproduce this expectation value, which is something like p squared over 2 plus the same expression. So I did it for the 2-point function. It should be clear to you that because correlation functions are determined by weak contractions, I can do the correlation function of any number of del x's, and it will map to the same correlation function on the ground state. If you look at composite operators like the stress tensor, as we discussed, there might be a little bit of renormalization due to normal ordering, but no big deal, you can follow through. But the big puzzle here is, if I want to really identify computations done here and here, what can I do that allows me to talk about non-trivial states in the past and in the future on the cylinder? Now, I really don't like to work with the plane that much. So before we continue, I want to discuss more wild transformations. So you should always worry a bit about working with CFTs in flat space, because a CFT is a gapless theory. So there must be all sorts of bizarre infrared effects. Defining the vacuum must actually be somewhat subtle. I mean, there are going to be very low energy states about the vacuum and all of that. A lot of the calculations you do in CFT are secretly done on a sphere. And that's what I'm going to discuss now. So let me do another wild transformation. Let's see. Actually, before I do that, so the cylinder treats the past and the future pretty symmetrically. But when I went to the plane, the past goes to the origin, while the future goes to infinity. So the cylinder has an obvious symmetry that exchanges past and future. If I try to do the same thing, if I try to track what happens to this symmetry in the plane, this is z to 1 over z. So this is clearly not a symmetry of the plane metric. It maps the plane to the plane metric to the z bar over z bar of absolute value of z to the 4th. So what's going on is that you get the r squared over r to the 4th plus 1 over r squared, the phi squared, and then you can do an r to 1 over r to go to the usual metric. So what we're learning is that if a wild factor goes to infinity as z to the 4th, it can map infinity to the origin smoothly. So now, suppose I want to compactify my plane. I want to get rid of, make infinity into a smooth point. But I also don't want to make something terrible happen at the origin. What could I do? Well, I could just look for a wild factor that blows up like z to the 4th at infinity, but does not blow up, does not blow up at the origin. Let's see. Can we write a good one? So did I not write it? Ha. Well, I hope I remember it. So I can try something like this. The z bar over 1 plus z squared squared. Why do I like it? I like it because it treats z behaves well under this symmetry, among other things. So it's a metric which is invariant under this transformation. So it treats the past and the future in the same way, if I think about it from the point of view of the cylinder. And actually, let me also write it down from the point of view of the cylinder. This becomes ds bar. There's going to be an e to the s plus s bar. And then we have a 1 plus e to the s plus s bar squared. So it's like ds bar over 2 cosh s plus s bar over 2 squared, or something like that. Anyway, it's a Weld factor that squeezes both ends of the cylinder. Can you guess what space is this?
Is this
Yes, it's the sphere. So this is the sphere. It's a sphere in essentially coordinates which are obtained like this. You can put the sphere on a plane and project. So a point z gets mapped to some point on the sphere. So again, we can do the same rigmarole. We could ask, if I take this kind of correlation function, or maybe this type of correlation function, and map it to the sphere, what does it represent? And we learned from here that if I put the ground states in the past, that's the same as sort of having a smooth geometry, nothing special happening. We're doing something which is invariant under exchanging past and future. So you can see that putting a 0 in the future must give you something which is smooth at z equal to infinity. So on the sphere, z equal to 0 is the north pole. And then there is one single point, the south pole, which I can call z equal to infinity. So the sphere gives you a compactification on the plane where you add one point at infinity, which I'll just call infinity. And this sort of correlation functions on a cylinder with the ground state in the past and in the future map directly to correlation functions on the sphere. So if I have on the plane a bunch of operators, this sort of map gives me correlation functions on a sphere with a bunch of operators. Placed away from infinity. So at infinity, you should say I have the identity operator. I'm not doing anything. So we've learned an interesting piece of dictionary, that to do calculations on a sphere, as long as I don't have operators at infinity, I can do calculations on the plane. And if I don't have any operators at 0 and at infinity, I can do calculations on a cylinder with a ground state. Where equality means that I might have to adjust what do I mean with an operator. Like here, what I call dx in one coordinate system might be a ds, might be dx times something in the other coordinate system. Okay. So now I would like to enrich this dictionary. I would like to figure out how to talk about situations where there is non-trivial state here, or vice versa, situations where there are operators sitting at 0 or at infinity. Mm-hmm.
What does it mean that you don't have any operators at 0 and infinity? How restrictive is that?
Well, these correlation functions are holomorphic functions. So if you know the correlation functions for positions away from 0 at infinity, you kind of know them automatically at 0 and infinity as well. So it's not restrictive at all. Okay. And indeed, what I want to do next is to say, OK, let me take the points away from the 0 and infinity and bring them there and see what happens here. So for example, so I can use this recipe. So in order to take the dzx as z and send it to dzx as 0, what I can do is I can take e to the minus s dsx as a function of s and send and then act on 0 to represent the fact that I didn't have a state, an operator at the origin to start with. And then I'm going to send s to minus infinity. Sorry, yes. We know what this dx is. Remember, there is sort of a sum of a n e to the ns, probably minus. I might be doing some mistakes with signs here. I hope not. This is a sum of term. There is an a minus 1. I still have an e to the minus s. I find the following things. I find an a minus 1 acting on the vacuum plus e to the s a minus 2 acting on the vacuum plus e to the 2s a to the minus 3 acting in the vacuum, and so on and so forth. As I send s to infinity, this gives me only the first term survives. So by this little calculation, you can show that having a minus 1, 0 in the cylinder is the same as having del x inserted at 0. And analogously, having a 1 on the ground state in the future is the same as putting the x at infinity, although you might have to understand how to do that. It's a limiting procedure. It's not a problem. We can take that as definition. I'm going to do calculations on a sphere, and when I put something at infinity, it's the same as doing the calculation on the cylinder and putting this in the future. You can just continue the procedure. You can ask yourself, OK, what happens if I put del x, the stress tensor, and I send z to 0? And you just build many more entries of the dictionary. I don't know, a minus 1 squared of 0 is equivalent to putting del x. A minus 2 of 0 is equivalent to putting del square x, and so on and so forth. So this is a big chunk of this so-called state operator map. State operator map instructs you on which states do you need to put on your cylinder in order to find a certain operator on the sphere, or vice versa. Now, at the moment, the state operator map does not look one-to-one at all. Like every familiar operator, I can write as a state, but there are some states which do not look like a familiar operator at all. So how do I talk about momentum modes? I mean, it's not super hard. If I were to build a momentum mode out of the vacuum, what would you do?
I think it's like e to ip.x or something. No?
Yes. That's correct. And where did x live? Where do we find little x? We found little x in the expansion of capital X, or the field. The zero mode of the field was little x. Something like this, plus dot, dot, dot. So, after you stare at this for a bit, you can sort of guess that you kind of need to look at something like e to the ipx. Now, how do we make sense of that? Can we make sense of that? Is that a sensible thing to do?
Well, I guess one would have to put like normal ordering or something, because then like when I expand it in a series.
Right. That's one thing we could do. How do we define this? One possibility is to normal order. Say on the cylinder, if we want to define it on the cylinder, we could try to normal order. But I think we learned that normal ordering is not a great thing to do on the cylinder. In flat space, it's pretty good. On the cylinder, not so much. So, okay, I should probably just do this. I say, okay, on the plane, we'll define it by normal ordering. I don't know what that actually means, right? What does it mean? Okay, what does it mean when I say I define it by normal ordering? Because remember, on the plane, it's not like we can expand in modes and say I put the creation operator to the left or to the right, or the destruction operator.
Because it means that if I put it in a correlator, I don't do big contractions with itself.
Absolutely, absolutely. So what this really means, it's a recipe to build a correlation function. That's the only way you should think about it. And that's what an operator is in quantum field theory. It's a recipe to get an answer. And the recipe is, if you have a correlation function, a bunch of other operators, do with contractions only with other operators. Don't we contract fields in the same exponent. It wouldn't make any sense because we infinity. So we could now use this prescription to do some calculations. For example, you could say, okay, what's the correlation function of e to the ipx normal order? I will not write the normal order. On the plane. At first sight, you could say, well, it's 1 because I have nothing to contract with, right? And we're just going to really think about this as a power series expansion. But we should be careful because we kind of put an e to the ipx for the zero mode, and we're integrating with the zero mode So actually, yeah, okay, here we start hitting the sort of unpleasantness of working on the plane. And then you can, but it's fine. Once you accept that sort of your total momentum must add to 0, then it's not difficult to do a calculation like this. You just need to patiently account for all possible recontractions. There is something like a 1 over n factorial, x to the n, p to the n, p to the minus p to the n, 1 over n factorial, so put an I, x to the n, right? And then I need to know which of these I contract with that. There is a one possible term for each permutation. So I get n factorial terms when I start contracting. And so I get something like a sum over n, p to the 2n. Then there is this sort of minus log of x z minus w squared to the n. And there is still a 1 over n factorial. So when the dust settles, you end up with something like 1 over z minus w absolute value squared to the p squared. What a weird result. It's weird because I find the fractional power of z minus w. This is very different from what we saw taking correlation functions of more familiar operators. So the reason this is happening is because this is an operator which has some kind of a multiplicative renormalization going on. So but so I say this. So in a sense, when you did this normal order, you okay. I think I want to show it in detail. Sorry, how does this operator transform when I change the coordinate system? But for now, I just want to say this is a beautiful example of an anomalous dimension. Okay, this is telling you the dimension of this, the scaling dimension of this operator is p squared over 2. And indeed, it is sort of the simplest way model of an operator which is a scaling dimension. Scaling dimensions are very important in conformal field theory and in quantum field theory. It's just a very striking fact that the dimension of things in the quantum theory is not the same as the dimension in the classical theory. This leads to all sorts of interesting phenomena. And this is sort of the simplest possible example. Now, we will see momentarily that when you do this state operator map, perhaps I should have done it already, the energy of the state maps to the scaling dimension of the operator. So a posteriori, this is a very good thing because this state we are trying to study has an energy p squared over 2. So it's reassuring to see that the scaling dimension of the operator we're trying to associate to it also has scaling dimension p squared over 2. Now, this definition is fine on the plane, but it's not really insightful. How could we try to regulate this expression? I kind of want to do a point splitting regularization of some sort. I will actually have to sort of smear things around. I could try to do something like that, where f is a bump function of some sort, something which is integral 1 and sort of supported on something of radius of size epsilon. Then, if I write this thing, I can definitely discuss what are the possible divergences I will encounter. Right? I can say, well, divergences will come from contractions of this operator with itself. And say this properly. So when I study a correlation function involving this operator, if I allow myself to take with contraction between the operator and itself, I will have, let's see, something like an x to the n, maybe, and I'm taking k contractions within, and there is going to be a bunch of combinatorics that I need to think about at first, because I have, I have a factor of 1 over n factorial, and I'm trying to select two groups of k things that I want to recontract. Let's see. So it's something like an n factorial over a k factorial times k factorial times n minus 2k factorial, perhaps. I don't think I'll get the combinatorics right, but let me try. And then each of the first group can be contracted with each of the second group. So this gives me a k factorial. So perhaps I get something like that. So sort of the dangerous terms seem to be involving a sum over n factorial over n minus 2k factorial. Sorry, 1 over k factorial. There is still going to be an n x to the n minus 2k that I have not contracted. And then there is going to be some logs of the propagator sort of thing to the k. And so you kind of see that this double sum factors. I get back an e to the I get back the same operator times the exponential of these. And so if I want to remove this potential divergence, I can take subtract something like p squared, an integral of f of epsilon of z, f epsilon of w, log of z minus w squared. Okay. So this quantity is going to be finite as I take f epsilon to 0, because I've removed all the possible problems. And this removal is multiplicative. I took my naive operator and I multiplied by something. And then I'm going to take an epsilon to 0 limit. Now, I did this calculation in some coordinate system. If I did it in a different coordinate system, the two will differ by an overall factor. A factor that looks like e to the p squared, integral of f of z, f of w, and then log of sort of, I don't know how to call new coordinates. Sorry. I don't know if I can do this in real time. Maybe I can. There is something like a z prime of z minus w prime of w, right, over z minus w squared. And this sort of has a finite limit as z and w are squished together. You pretty much get logarithm of the Jacobian. And so you get e to the logarithm of the Jacobian. And so you find that the operator e to the IPX in some coordinate system transforms as the z prime over the z to the p squared e to the IPX z prime, something like that. So it transforms like, so this kind of transformation is called a transformation of a primary field in conformal field theory. It's a transformation very similar to the one of del X, except that there is a power p squared over 2 for the holomorphic Jacobian and p squared over 2 for the anti-holomorphic one. So, okay, so we've learned how to use these vertex operators, sorry. And this operator represents states with momentum. And now you can repeat the argument to figure out what happens if I do something like, I don't know, a minus 1 on p. Well, that will map to something like del x e to the IPX, which is again kind of defined by not taking contractions between the two in the plane, and so on and so forth. So we're now in a pretty good state, because if we want to do the calculation we are aiming to, sorry, which is the calculation of something like this, with some states, we can pick a Weyl factor which squeezes this by the correct exponential amount, the same way as for the cylinder. And this calculation will now map to a sphere where each of these tubes has been replaced by the corresponding operator. So by using the state operator map, we can convert this picture into this picture. And once we are here, it's a correlation function on a sphere, which is the same as a correlation function on a plane or on a cylinder. So we know how to do it. So now we're in a reasonably good place. Now, where does the complex structure of this surface go? Complex structure is invariant of the Weyl transformation, so it must be going somewhere here. And the only thing it can go to is the positions of these points on a sphere. So as long as I don't have complicated genus, as long as I have no holes in my surface, it's just sort of tree-level in string theory, I can always map to a sphere. And the only thing I need, the complex structure I need to integrate on, it's called the puncture sphere, a sphere with a bunch of points, is the position of the points. Now, if I were to do more complicated calculations, like a one-loop calculation, well, then I would have to work harder. You know, if I have something like this, then I will have to, the best I can do is to map it to a donut with 4 points, for example. And then I had to learn how to make safety calculation on a torus, and so on. So that's a bit harder. But in this course, we'll only look at the tree-level case. Okay, sorry, I think I need to do with a phone call. So I will leave questions for the next lecture.